Welcome to the Deep Dive. We're here to crack open some really compelling sources and, distill them into pure insight for you. So today, we're tackling a challenge that might take you right back to your high school days, maybe even college calculus. Imagine looking at a really complex calculus problem, one of those multi-layered integrals, powers, fractions, the whole deal. Maybe something like the integral of 5 by 4 over 1 by 2 to the 5/2 power dx. Now, honestly, could you solve that in your head right now? Probably not without, some serious head scratching, right? But here's the deeper question, and it's really what we're going to wrestle with today. If a computer program could just knock that integral out, like in a blink, would you consider that program intelligent? So yeah, we're plunging into this fascinating world of problem solving, human problem solving, artificial problem solving, how we actually dismantle these complex challenges, and what that really reveals about intelligence itself. Our insights today, they're drawn from a classic MIT lecture. It takes us way back, really, to the roots of AI and problem-solving theory. We're looking at the kind of thinking needed for those calculus problems you might, loved or maybe loathed, but from a totally new angle, a more empowering one, I think.
That's right. And what's so powerful about the source material is how it shines a light on something we all do, often without even realizing it. The way we instinctively tackle complex problems like that integral you mentioned. We don't usually think about how we're doing it. We just do it. But once we actually name these techniques, understand their structure, we gain this immense power over them. They stop being just intuition and become like deliberate skills we can deploy.
Ah, okay. So it's about seeing the hidden architecture behind how we think. And the core idea here, you're saying, is called problem reduction.
Exactly. Problem reduction. The basic idea is you take a really daunting problem and you apply what's called a transform to it. Think of these transforms as, strategic moves. They convert the big, scary problem into a different one, hopefully simpler. And the goal, it's to keep chipping away at it, simplifying it until the pieces are so basic you can just, look up the answer in your head, like a mental table of solutions you already know.
That's a neat analogy, taking a giant tangled ball of yarn and knowing just how to untangle it knot by knot until you have these nice, neat, individual threads.
Yeah, that's a great way to put it. And when we talk about these transforms, we can actually group them into two main types. This is where the framework really starts to show its power. First, we have what are called safe transformations.
Safe transformations. Okay.
These are like the bedrock rules. Always reliable, guaranteed to work. They'll never lead you down the wrong path. Think of them as like mathematical certainties.
So the no-brainers, the reliable workhorses you can always count on. Can you give us a feel for what those actually look like in calculus?
Absolutely. Think about some of the very first rules you learn. Like if you have an integral with a constant multiplied by a function, you can always just pull that constant out front, right? Or if you're integrating a sum of two functions, you can always break that into the sum of two separate integrals.
Right, standard stuff.
Exactly. These are maneuvers that always simplify or break down the problem reliably. Oh, and another crucial one. If you're integrating a fraction, like a polynomial over another polynomial, and the degree of the top polynomial is higher than the bottom one, you must do polynomial division first. It's like a knee-jerk reaction, but it's a guaranteed simplification. Always a winning move.
Okay, so those are the fundamentals, the operations you do almost without thinking. But what about the other kind of transformation, the ones where it's maybe not so clear-cut?
Right. Those are the heuristic transformations. Now, these are where things get really interesting, and maybe where a lot of what we perceive as human intelligence comes into play. These are methods that, they often work. They can be incredibly helpful, but they come with no guarantees.
No guarantees?
Nope. They might be brilliant shortcuts, or they might lead you straight into a dead end, forcing you to backtrack. They're more like attempts, calculated gambles. Not strict algorithms. You can't really solve the truly complex problems without them, but you also can't just apply them blindly.
Okay, so these are the more creative leaps. The educated guesses that might save you a ton of time, but they also require some strategy. What are some examples of these more adventurous moves?
Well, a classic example is what we call trigonometric rewrites. If you're faced with a messy integral, maybe involving tangents, cosecants, seconds.
Yeah, those get tricky.
A common heuristic is to just rewrite everything in terms of sines and cosines. Now, it doesn't always simplify things, but it's often a good path to try. It can consolidate the problem into a form that feels more familiar. Another one If you see tangent x inside an integral, a heuristic is to try substituting y equals tangent x.
Okay.
This basically transforms the problem. It goes from being trigonometric to being polynomial, which, often feels a bit more manageable. And then there's the really famous one, the 1/2 heuristic. When you spot that pattern,
Oh, yeah, I remember that one.
right, your brain immediately screams, think trig. Because of that identity, cosine 2 plus sine 2 equals 1, so you try substituting x equals sine y. That often simplifies the integral dramatically. These are those aha moments you learn to look for.
Right, right. So, okay, we're applying these transforms, sometimes the safe guaranteed ones, sometimes these clever, maybe slightly risky heuristics. But this isn't just a straight line of steps, is it? It actually starts to map out, like, our decision process.
Precisely. And what's so powerful here is that this whole process creates a kind of graphical picture of your problem-solving journey. Think about planning a big project. If you have one main task, but it breaks down into several subtasks, and all of those subtasks absolutely must be completed for the project to work.
Okay.
We call that point an and node. In our problem-solving map, maybe you draw like an arc connecting those branches just to show they're all necessary.
An and node, got it.
But on the other hand, what if you have a problem and maybe there are, say, 3 different ways you could approach it? Any one of those ways will work. You just need to pick the best path.
Ah, like forks in the road.
Exactly. Those are or nodes. They represent choices, different routes to the same solution. You don't really care which one works in the end, just that one of them does.
So it's like we're building a decision tree as we solve the problem. And this structure, this map of our goals and sub-goals, it has a few names, right? You called it a problem reduction tree or an and/or tree or a goal tree.
Yeah, all those terms mean basically the same thing. The specific name isn't really the crucial part. It's the idea itself that by naming this process, by visualizing it, we gain a kind of control over it. And this immediately brings up a really critical question for any smart problem solver, whether it's a human or a machine. When you get to one of those OR nodes and you're facing multiple potential paths, how do you decide which one to take?
Right. You'd want to pick the easiest one, I guess.
Naturally, yeah, you'd want to tackle the easiest looking subproblem first.
But easiest.
Yeah.
It feels so subjective. How do you actually quantify that for, say, a computer program?
Well, that's the brilliance of some of the early AI work we're looking at today. The pioneering program we're about to discuss used a very objective, very measurable metric. It's called depth of functional composition.
Depth of functional composition.
Okay, what's that? It basically just counts how many functions are nested inside each other. So, for instance, sine cosine x is deeper or more functionally composed than just sine x.
I see.
By measuring this depth, the program had a concrete way to figure out which path looked simpler and therefore maybe more promising. It's kind of like measuring how many layers are in an onion. Fewer layers often means it's simpler to deal with.
That's clever. And this brings us neatly to, well, a truly historic moment in the dawn of AI. We're talking 1960, MIT. There was this brilliant, nearly blind graduate student named James Slagle.
James Slagle, yeah.
And he developed an AI program specifically for this task, symbolic integration. This program, written in Lisp, apparently it's so foundational that people in the field sometimes call it a one-lecture course in artificial intelligence.
That's true. It really anticipated so many core concepts that shaped the field for decades to come.
And what makes Slagle's achievement just mind-blowing are the constraints he was under. And you have to imagine building something this groundbreaking on what they call an antique computer.
Oh, absolutely, with almost no memory. The sources mention it had, get this, 32 kilobytes of memory.
32K. That's less than a tiny icon file today.
Exactly. It's staggering. And, almost no speed by our standards. Yet somehow he built a system that could solve problems that stumped a lot of very smart humans.
So what was the secret sauce then? How did this program, with practically no resources, manage to tackle these complex calculus problems? Can you give us sort of a simplified look at how it worked?
Sure. The program followed this surprisingly elegant loop. It was really quite clever. First, it would apply all the safe transformations it knew. The guaranteed wins we talked about.
Right, the bedrock rules.
Second, after doing those initial simplifications, it would check. Can the main problem, or any of the new subproblems it just created, be found in its internal table of integrals? That's its lookup sheet of basic known solutions.
Okay, so look it up.
Yeah. If it found an answer, great. It reported success and essentially pruned that branch off the problem tree. Done. But if not, then it would scan its whole goal tree, find the simplest unsolved problem sitting at one of the leaf nodes using that depth of functional composition metric we mentioned.
Right, find the easiest loose end.
Exactly. And then, crucially, it would apply one heuristic transformation to that simplest problem. Just one.
Only one heuristic at a time.
Just one. Then it would loop right back to the beginning, step one, reapply safe transforms, check the tables again, and so on.
That's a really smart design choice, actually, applying only one heuristic before reassessing the whole situation. It makes perfect sense, given that heuristics are those risky gambles, right?
Exactly right. You wouldn't want to chain a bunch of potentially wrong turns together without stopping to see if you're actually getting somewhere useful.
So, how did it do, this dawn-age program, facing tough MIT calculus problems?
The results were, well, nothing short of phenomenal, especially considering the era. When they benchmarked it against freshmen in MIT's main calculus course, 18.01, it performed remarkably well. They gave it 56 of the hardest problems from past final exams.
56 tough ones. Okay.
It solved an astonishing 54 out of 56 correctly.
Wow. 54 out of 56. That's incredible. What about the two it missed?
Well, and this is what's truly insightful. Its failures weren't because of some flaw in its intelligence or its problem-solving strategy. It simply lacked two specific transformations that were needed for those particular problems.
So it wasn't that it ran out of memory or got stuck.
No. It didn't run out of its tiny memory. It didn't get stuck in some infinite loop. It just needed a couple more tools in its toolbox. And that was a really profound lesson for early AI researchers. Sometimes progress isn't about deeper reasoning, it's just about having more comprehensive knowledge.
That's amazing. A real testament to what a structured approach, even a relatively simple one, can achieve. So, okay, beyond the program itself, what did this work reveal about the domain of calculus itself? Were there surprising insights just from seeing how the system navigated it?
Yeah, this is where we learn about the nature of the problem space, not just the program solving it. For typical freshman calculus problems, like the ones on those MIT finals, the average depth of the goal tree, that problem reduction map we talked about, it was surprisingly shallow, only about 3 levels deep on average.
Only 3. Huh.
Which suggests that these problems, which can feel incredibly complex when you're a student wrestling with them, are actually structurally not very complicated for, let's say, ordinary mortals once they master the reduction process. And even more interesting, on average, only about one branch of that whole goal tree ended up going unused.
Only one dead end, typically.
Pretty much, which means the problem reduction tree doesn't usually grow into this massive, bushy tangle of useless paths and dead ends. And the implication there is kind of subtle but important. It means that the choice of which path to take at an OR node, remember, using that depth of functional composition metric, while it seems sophisticated, it probably didn't actually matter as much as you might think. At least not in this specific domain.
How so?
Because most paths apparently led pretty quickly either to a solution or to an obvious dead end. So you weren't often heavily penalized for making a slightly suboptimal choice early on. The structure of the domain itself was forgiving, in a way.
Interesting. So in this calculus world, a lot of what feels like really complex decision-making might actually be more straightforward structurally than we perceive. Which leads us, I think, to a really crucial meta lesson from all this. Something the sources call the catechism of knowledge.
Yes, exactly. It shifts the focus from the specific problem integration to a kind of universal toolkit for understanding and approaching any complex field. It's about asking a series of vital questions about the knowledge itself, kind of like a checklist.
Okay, what are these questions?
First, what kind of knowledge is involved? Is it facts, rules, procedures? For symbolic integration, we saw its knowledge about transformations, about goal trees, about looking things up in tables. For, say, medical diagnosis, it would be different kinds of knowledge.
Right, what kind of knowledge? What's next?
Second, how is that knowledge represented? Is it in text, in equations, in diagrams, in Slagel's program, graphs or logic, or just natural language?
Right, representation. Third,
how is it used? How does the knowledge actually get applied to reach the goal? We saw transformations simplify things, table lookups prune off branches of the problem. How does the knowledge do work?
how it's used. Makes sense. And the last one.
And finally, this is often the most surprising one, how much knowledge is actually required?
Yeah.
Oh.
That one really does seem eye-opening. We usually assume you need just vast amounts of information to master something complex.
We do. But the truly astonishing revelation from Schlegel's work was, as we said, his program only needed that table of 26 basic integral elements.
26, that's it.
And it had about 12 safe transformations and maybe 12 heuristic ones. These relatively few bits and pieces of knowledge, when structured correctly and applied strategically, were enough to ace an MIT calculus final.
Wow.
It wasn't about knowing endless facts. It was about having the right knowledge, well organized, and knowing how to use it effectively.
That's a powerful idea. And this understanding, this focus on how knowledge works, it led to some incredible advancements later, right?
Yeah.
The sources mentioned Joel Moses.
That's right. Joel Moses, who later became MIT provost, built on this. He developed things like a diagonal table approach, mapping specific integration methods to the characteristics of the problem itself. This led to programs that could consistently beat expert human mathematicians at integration.
And the descendants of those programs are still used today, aren't they, in tools like MATLAB and Mathematica?
Absolutely. They form the core of many powerful symbolic math systems we rely on now. It all comes back to this idea of meta-knowledge. Understanding how knowledge works, how to represent it, how to organize it, that's what makes you smarter when facing any new domain. It's empowering.
Which loops us all the way back to our very first question, doesn't it? Is a program that can solve one of those intimidating integrals? Is it truly intelligent? Many of us, I think, especially remembering our own struggles with calculus, might instinctively say, yeah, of course it is. That's hard.
And here we hit this really profound paradox. It's sort of the core insight from this whole deep dive. When we truly understand how something works, how it's broken down, how it's solved step by step, its perceived intelligence often, well, diminishes.
It loses its magic.
Kind of, yeah. Think about seeing a friend just effortlessly solve some tricky puzzle. They seem brilliant, right? But then they explain that process, show you the steps, and suddenly the magic evaporates. It just seems like a logical sequence of moves anyone could follow if they knew them.
Right. It's like watching a magician do an impossible trick and then getting to go backstage and seeing the mirrors and the wires. The wonder shifts from, how did they do that, to, oh, that's clever.
Exactly. And our sources share this fantastic anecdote that just perfectly illustrates this point. There was this student initially pretty skeptical about computer intelligence.
Okay.
He was shown Schlegel's program solving one hard integration problem after another. And after seeing its prowess, he sort of conceded, okay, maybe computers can be intelligent. I'm learning how to do that stuff, and it's definitely not always easy.
So he was convinced.
Momentarily. But then, the professor telling the story said he made a fatal mistake. He spent the next hour meticulously explaining how the program actually worked. You know, the problem reduction, the safe and heuristic transforms, the gold tree, the simple metrics, all the stuff we've been talking about.
Okay.
And at the end of that hour-long explanation, the student famously took it all back. He said, you know what? I take it back. It's not intelligent after all.
Why?
It does integration the same way I do.
Wow. That's the mic drop moment, isn't it?
It really is.
It just strips away all the mystery and replaces it with understanding. And the real power, like we've been saying, isn't just piling up facts. It's that knowledge about knowledge is where the real power is.
That's the core takeaway. Understanding the underlying processes, the structures, how information is categorized and used, that's what truly empowers us. Both to solve problems ourselves and maybe to think more critically about what we even mean by intelligence.
So, as we wrap up this deep dive, it's worth taking a moment maybe to reflect on that. How understanding the mechanics of problem solving, whether it's for calculus or, frankly, any other daunting task, can profoundly change how we see its difficulty and maybe the intelligence we thought was required to conquer it.
And that leaves us with, well, a provocative thought to chew on. What other skills or abilities, maybe ones you have or ones you see in others, do you currently think of as intelligent, or maybe even a bit mysterious, simply because you haven't really broken them down into their fundamental parts yet? How might applying this catechism of knowledge, asking what kind of knowledge is involved, how it's represented, how it's used, and crucially, how much is really needed? How might that apply to a challenge you're facing right now? You might just discover its true complexity is far more manageable and its solution much more accessible than you ever imagined.